All right, this is lesson 7.3, exponential functions from graphs and tables. Our objective is that you'll be able to create exponential functions from graphs and tables. In other words, if I give you a graph or if I give you a table, you should be able to give me an exponential function, something that looks like this, that matches the table or graph that I gave you. Remember from 7.2 that exponential functions are of this form: f of x equals a times r to the power of x. That's the important thing, is that the variable x is in the exponent. You should know that a is our y-intercept, or sometimes called our initial value, and r is our ratio. It's also called the factor. It's either a growth factor if r is bigger than 1, or a decay factor if r is less than 1. Finally, remember from 7.2 that for the purposes of our Math 1 class, a and r are always going to be positive. In future math classes, you might have them be negative, but that will not be the case for this class. Here's the directions for the 5 practice problems in these notes. I want you to write an exponential function for each given table and graph. I want to point out that we're assuming the function is exponential. If I gave you this graph and I just said write a function, or maybe we're playing the guess what's the function game, and you only have 2 inputs going to 2 different outputs, this could be linear. This could be the line that has a y-intercept of 3 and also goes through 1, 5. But we're just going to assume the function is exponential. Since we're assuming it's exponential, we're going to write it in that form, a times r to the x. You should notice right away, this is a valuable piece of information that the table is giving us. It's giving us the y-intercept. That would have been valuable even if this was a line, but again, we're assuming it's exponential. Since we're given the y-intercept, we're given the a value already. So that means our function, see how it's called g of x, so I'm going to use g. Doesn't really matter. Our function is going to be 3 times some r number to the power of x. The problem is we don't know what r is yet. And again, when you write your exponential function, I need you to give me a number for a and a number for r. They can't stay a or r. So we're halfway there. How do we find r, though? Well, we're going to use this second point that we're given to find r. So this is saying that when x is 1, our output is 5. In other words, g of 1 is 5. Now what we're going to do next is g of 1, we know it has to look something like this, just with x being 1 instead. So we can rewrite that. The 5 is going to stay there on the right side. But g of 1, because we know it's exponential, can be written as 3 times some ratio we don't know yet, but we know it's g of 1, so we're just going to plug in a 1 for x. Now we have an equation where everything is just a number except for the variable r. So we can solve for r. If we divide both sides by 3, then the left side of the equation is just going to be r to the first power, which is really just r, and the right side of the equation is going to be 5 divided by 3. I'm just going to erase this 1 because r to the first power is just r. And now we have our 2 pieces of information that we need to write our exponential function. So the function that matches this table is the function g of x equals 3 times 5/3. Oops. There we go. To the power of x. All right, let's try another one. Again, we are very fortunate that it gives us the y-intercept. So we know that a is 15 for this problem. And then the second point, it just tells us that g of 1 is 3. Now again, g of 1 can be rewritten, right? So g of 1 is going to be our a value times r to the x, but we know our a value is 15. 15 times r to the, since g of 1, since x is 1, I'm going to plug in a 1 where I would normally write x. And that's going to equal the output, 3. Again, all we got to do is divide both sides by 15. And we'll get r to the first power equals 3 divided by 15. R to the first power is just r, and 3/15 reduces, that's 1/5. So we have our r value, we have our a value, so we can write our function. A times r to the power of x. So we have one function that represents growth, because r is bigger than 1. Another function that represents decay, because r is less than 1. All right, try this last table on your own, and then come back and check your work. Okay. Hopefully you found that the initial value, the y-intercept, is 2. And our growth factor is also 2. So your function should look something like that. All right. Let's switch over to graphs. It's the same idea, though. It's just you're given a graph instead of a table. We can see our y-intercept, our starting value, our a value is 4. And then we have the point 1, 2. In other words, that means, I'll just use f for function this time, f of 1 equals 2. All right, so since a is 4, we know that f of x is going to be 4 times some common ratio to the power of x, which means f of 1 is 4 times r to the power of 1. Problem is we still don't know what r is. We do know this, though. We know that f of 1 is 2. So I can take this equation that we put together, solve it for r by dividing both sides by 4, and I will get that r is 2 divided by 4. I'm not going to write 2/4. I hope you can bear with me. I'm going to do 2 steps in one. 2/4 is the same as 1/2. So that's our r value. We already know our a value. So the function represented by this graph is f of x equals 4 times our common ratio to the power of x. Try the second graph on your own and come back and check your work. Okay. Hopefully you picked out that initial value, or y-intercept, is 3. We have another point, 1, 6. So we should end up with a equals 3. We'll find that r is 2. So we have the function 3 times 2 to the power of x. All right, and that's it for our notes. I do want to move into the practice problems this time. You're going to have some con skills that ask you to write functions about exponential decay. And so you'll see wording like the population drops by 5% every year, or loses 30% of its value per year, or loses 10% of its mass every, in this case, millennium instead of year, but every unit of time, right? So what I want you to write in your notes is that if you see that kind of phrasing where it drops by so much percent each year, and really it doesn't have to be year, it could be every decade or every millennium or whatever it is, but some unit of time. If you see that, let's just call it P for percent. If it drops by P percent each year, all that means is that your growth, or rather your decay factor, R, is going to be 1 minus, I'm going to write P over 100 here. It makes it look more complicated than it actually is, though. That's just the percent written as a decimal. The way you can think of it is this is saying you're going to keep 100% of what it used to be, and then you're dropping or subtracting that percentage that you're losing, right? So let's try it here. It says that the population drops by 5% every year, so our ratio is going to be 1 minus 5 over 100. It really just as a decimal, it's 0.05, 5 hundredths. That's our R value. Our A value is the current population. It's 200. So this is our 200 times R to the power of X. You probably won't write it this way. This is pulled straight from Khan Academy. If it's multiple choice, you probably need to rewrite it as 200 times, you can subtract that. That's 100% minus 5%, that's 95%, or 0.95 to the power of X. All right, if you have any questions, ask them at the end of the video, or make up your own, and I will see you all in the next one.